So welcome to Math 238. This is a little introductory video to just the idea or what is differential equations all about. And actually, differential equations is one of the most applicable topics of mathematics because, and for that reason, there's a lot of different ways to approach differential equations. I'm going to come at this from a modeling perspective. So the idea is that a big part of this class is going to be about modeling situations using differential equations. So first of all, what is a differential equation? Okay, a differential equation is just simply an equation that involves a derivative. Simple. So most of your lives you have dealt with equations that were not differential equations, they're just equations. If you took Calc 1, when you're dealing with when you did related rates, usually we took equation and there'd be some derivatives left in the equation, or when you did explicit differentiation, we also would, when you took the derivative of two sides of the equation, it would produce a differential equation, an equation with derivatives in it. So when we talk about solving differential equations, that means we're taking an equation with derivatives in it, and we want to find a function whose derivative would make that equation true. So when we're modeling using differential equations, that means that we're modeling with equations that have derivatives in them. So we're going to start off by, before we get into the different types of different equations, we're going to just talk about what we mean by modeling. So when you try to model something, and this is the main reason the math is created, is to try to get a handle on what's going on in the real world. So when we try to model something, we're not looking for an exact copy necessarily. We're looking for something that has some of the characteristics or natures of the thing we're trying to model. So like, for example, a photograph, a statue, and a dog could all be possible models of a human being. The photograph is modeling what the human looks like, but it has no depth or thickness or life to it. A statue gives us some 3D picture of what a human looks like, but there's nothing, none of the life or organs in it. And a dog, of course, doesn't really look like a human being, and it's a lot different than a human being. It's a completely different animal. Yet it is alive and has some of the same organs and some of the same body parts. So again, all these are models of a human being. They're all, of course, lacking in completeness, but nonetheless, they do help us give us some ideas of what a human is like. And which one of these is best? Well, it depends on what you're trying to do. If you're just trying to get a picture of what the person looks like, then the photo is probably best. If you're trying to study the biology of human beings, then the dog is probably going to be a better model. So usually when we're talking about models, though, in this class, we're going to be talking about some mathematical models, so things that are happening mathematically, and within those models, there's a lot of things that can affect them. So, for example, if we're talking about we're trying to come up with a model for a rabbit population. Well, there's a lot of different things that affect the rabbit population. Like, it depends on the number of bobcats and coyotes and cougars and other types of predators in the area. It also depends on mice and other things that those predators might eat instead of the rabbits. It could have to do with the number of farms around the area. Weather, of course, has a effect on it, because droughts can lead to populations dying off, and even disease. You never know. There could be a disease that comes through and can have a drastic effect on the rabbit population. So there's a lot of, usually when we're trying to model something in real life, they can be very complicated. And so often what we'll do is try to limit the things that we're considering to make the model simpler. Okay. And then usually when we come up with a model, we use that model to predict, possibly future things that might happen, or even things that have already happened, and so we can compare with data. So often when you build a model, you want to use it to predict things that we already know, compare them to the actual data, and then you can use that to adjust your model to make it more, to make it better. And we use model for different things. Sometimes we're using models to have some very precise predictions, and other times we're just looking for a more so that would be a quantitative. So let's write that down. That's important. Qualitative versus quantitative. Quantitative. So the quantitative is maybe we have a model where we have a very precise law of physics or chemistry or something like that we know is pretty accurate. We can use that to actually come up with numbers. Qualitative is more like we might have a decent but very simple model of a rabbit population. We're just going to use it to find out whether the numbers are increasing or decreasing. We're not trying to get any more sophisticated than that. So qualitative is more kind of what is the quality? Is this population getting bigger, or is it getting smaller? Is it headed towards dying off? Is it headed towards getting too big for the area that it lives in, etc.? Whereas quantitative is more precise measurements. So things to think about when you're building a model. So when you're trying to build a model, and these are again just some general ideas as we move into the course. To build a model, there's really kind of a three-step process. The first step is to clearly state assumptions. So when you clearly state assumptions, basically you're looking at a model, this is kind of the science part of it. You're looking into what's going on, possibly looking at some data, and you're trying to come up with some assumptions that you think are true. And they are called assumptions because we don't know if they're true. We sometimes we have varying levels of confidence in that. So we're looking at different things that are measurable in the system, and we're going to make assumptions about that. Okay, so then the second step is to describe kind of all the players in the model. It looks like a P. Describe all the players. And so usually that's made up of both variables. You guys are familiar with variables, both independent and dependent, and also parameters. And we'll discuss kind of the difference between those in a minute here. So we're describing them, usually like labeling them, and this is the kind of building blocks we're going to use to make the model based on our assumptions. So then the third step in building a model is, as I just said, we're going to use our assumptions to derive equations. Relating the stuff in step 2. So that's the basic idea of, and I'm going to look at each one of those steps a little more clearly. So in step 1, we're trying to describe how some physical system works, and looking at the important aspects. So for example, the type of assumption we might come up with is that rabbits are not bothered by overcrowding. In other words, they can have as many rabbits as they want in a certain area. So that would govern the way we make our assumption, or the way we write our equation, our model. Or we could have something really precise, like some formula like work equals force times distance, or So we may be looking at a situation where we know some very detailed information about, or we may be looking at a situation where we just have some general ideas. And so we're going to take whatever information we have and come up with some assumptions that we believe to be true. Sometimes we know they're true because of laws of physics or something like that. Other times we're just speculating that we think they're true just by observations that we've made. So step 2, sorry, that was step 1. Step 2, again, we said there's independent variables, and that is almost always time. In our class, it's going to mostly be time. And then we have dependent variables. So usually there's one independent variable. Should have said variable. Then we could have one or more dependent variables. And these are all functions, usually functions of time, or of the independent variable. So these are things that change. When we say they're a function of time, that means these are variables that change as time changes. So like we talked about earlier, the rabbit population, that would be a variable that's changing as time goes on. Okay? And then there's one other one that's also a variable, but it's a different type of variable. So we call it a parameter. This is something that changes possibly from model to model, but it doesn't change with time. So maybe if we're looking at a certain rabbit population, it has a certain growth rate. That would be a parameter. So the growth rate for this rabbit population is set, but if you're looking at some other rabbit population, it would be different. But it doesn't change with time. So that's a parameter. Or you could say the initial population of the rabbit population. That's a parameter that's different from population to population or different from model to model, but it's not changing with respect to time in this model. Okay, so that's the difference between parameters and variables. Variables are, we have an independent variable, and we have dependent variables that are changing with respect to the independent variable. These parameters could be adjusted by the scientist that's making the model just to make it more accurate. Like maybe assume that the growth population is or the growth rate is a certain number, and when we try out our model, we find out that it's not as accurate as we'd liked it to be, so then we can go back and possibly change that parameter to make it better. Okay, so then in step 3, really our goal is, because we're going to be modeling differential equations, our goal is to describe the behavior of the dependent variable as the independent variable changes. That's basically what this step 3 is about. We're going to do that, of course, by writing an equation. And in this case, because it's the differential equation class, they're going to involve derivatives. So when you're looking at a certain situation, because we're planning on writing an equation with derivatives in it, of course, you remember hopefully from Calc 1, some of these words that give away a derivative, like rate of change and acceleration and velocity and flow rate, things like that. Things that describe a rate of change, we know would be represented by a variable in an equation. Okay, so I'm going to stop here in this video, and I'm going to follow up real quick with a second video that gives you some examples of what we're talking about. Hopefully this is just a general introduction to the concept of modeling and differential equations.